Hello everyone, welcome to this webinar on concentrated solar power cost analysis. Well, here today we have two experts on different aspects of concentrated solar power, and you'll have the chance to hear the presentations and also to ask questions. So sharpen your pencils, to ask questions at the end. We'll wait for a minute or so before we start, and just make yourselves comfortable, and we will get started shortly in a minute or so. In the meantime, you can have a look at the different options you have on the webinar platform, and you'll see the questions and answers box, and then you can pose your questions there. After we'll have a discussion with the panelists once they have both presented, and just make yourself comfortable with the webinar platform. Can see that a few of you are still joining, but I think it's probably time to get started. So, well, welcome to this webinar. So today we'll be covering concentrated solar power costs and water consumption innovation with NREL and Cranfield University. So we'll have Parthiv Kurup, CSP Cost and Systems Analyst at NREL, and Professor Chris Sansom from the Head of Center Renewable Energy Systems at Cranfield University. Myself, I'm Carlos Marquez, the Director of Market Intelligence at ATA Insights, and I'll be your moderator today. So could we start? I'll just like to ask the presenters to briefly introduce themselves in a couple of sentences. So Chris, would you mind introducing yourself?
Yes, certainly. Well, hello, everybody. Yes, my name is Chris Sansom, and I'm Professor of Concentrating Solar Power at Cranfield University. I've been at Cranfield for 12 years. Before that, I worked in industry for many years, and I have quite a large team of people working at Cranfield on CSP, and we're going to tell you something today about some of the work that we're doing currently on reducing water consumption in CSP plants.
Thank you very much, Chris. And Parthiv, if you could introduce yourself and then get ready to present as well, as you'll be first.
Thank you so much, Carlos. Good morning, all. This is Parthiv Kurup from the National Renewable Energy Laboratory. I'll be presenting some of the work that we're doing here, but also some of the research pathways that the Department of Energy are funding to be able to reduce the cost of CSP towards a much lower perspective than today. And I'm really glad to be able to speak with everyone today.
Thank you very much, Parthiv. So if you could share your presentation, and then without further delay, we'll get started.
How's that?
So if you could put it on full screen at the moment, yeah. I can your presentation. There we go. That works. Great.
Excellent. So why is this not? So today I'll be speaking about CSP and specifically costs and some of the trends that we're seeing right now. I've actually put together a presentation on some of the topics highlighted. So it'll be looking at costs currently, why are CSP costs decreasing, which is important, the annual technology baseline, and some of the cost projections, the CSP expansion potential to 20 2030 and 2050 in the United States, some current work that I'm looking at, which is looking at cost benchmarking as well, and then finally a DOE, a Department of Energy R&D pathway for high temperature CSP. And I have to really thank a lot of my colleagues as well for giving me some of the slides and really helping put this together as well. There's so much amazing stuff happening. I'll keep this to about 20 minutes or so and then hand over to Carlos and Chris as well, with plenty of time for questions at the end. So if we look at the first topic, the costs of CSP currently, I'll just highlight some of the NREL analysis and also some of the public information. By the way, this is important from an overall perspective, just to show the CapEx ranges which are being compiled by organizations like New Energy Update or CSP Today. I will be sending out the slides, so no need to try and scribble everything down right now. The main takeaway is that both power tower and parabolic trough are seeing a range of CapExes, which are decreasing as well. And these are just to highlight that there are movements in China, in Australia, Chile, and United Arab Emirates, for example. When you look at the power tower, the investment CapEx range is on the order of 3,300 to 6,200 per kilowatt, depending on how much of storage and how good the DNI is. So for example, the Dubai plant has approximately $5,400 per kilowatt. That's just the tower portion. Similarly, parabolic troughs are actually also in a similar investment range, around $4,200 to about $6,200 per kilowatt. As of last year, there were actually 2 molten salt power towers, molten salt troughs being built in China, but the status of those currently is a little shaky, so we're not fully sure about that. All of this is reported in the NREL report, and that'll be provided in the link at the bottom. This is the overall summary of why, one of the reasons we are looking at developing a cost perspective is to be able to add input into the System Advisor Model, or SAM. So SAM 2018 and SAM 2019 have had their specific inputs, such as the heliostat field and the thermal energy storage, changed based on the work and the connections to industry and the surveys that we're doing, both from the US perspective and also from the global perspective. So key ones to highlight, for example, are the heliostat field currently in SAM 2018 and SAM 2019 is $140 per meter squared. Similarly, the solar field on the parabolic trough side is about $150 per meter squared installed. That's everything installed. The System Advisor Model has had improvements also in the thermal energy storage cost, as well as the power cycle cost and balance of systems cost for both the parabolic trough and molten salt power tower. These costs are then reflected in each of those cost components for the System Advisor Model, which you can then use to be able to put together rough costs of a pre-build situation. Again, all of this detail is provided in the report, which just came out actually this year. So we'll make sure that you have the link for that. Knowing that CSP costs have been reduced significantly, I thought I'd just highlight some of the reasonings for the IRENA analysis and also some of the movements that are happening in the world. When we look at 2010 to 2018, the average cost of CSP has been decreasing in terms of a capex and also a levelized cost of electricity perspective. So for example, from 2017 to 2018, the global average reduced by about 26% in the IRENA databases and data. But really, why is that the case? And there are many good reasons for that, such as the increased commoditization, increased modularization, increased size. For example, the Dubai 700 megawatt plant, which has both an increased size as well as a 35-year PPA, which is fantastic for decreasing the levelized cost of electricity. Another important shift and trend which is being seen in the world is the emergence of large PV and CSP co-located and hybridized plants, such as the Noor Medelt 400 megawatt phase 1 plant. Very important when you're looking at reducing the cost of CSP by using the low-cost PV and the storage capability of CSP to be able to really drive down the average cost of production. Another key driver that's being seen in the market is, for example, plants being built and now being really finished in high DNI areas like in Chile. For example, the Cerro Dominador plant, which also is a PV CSP plant. Again, improved manufacturing and volumes of scale are certainly beginning to show important drivers in the market as well. When we look at some of the further detail behind this, one of the key things is that the decreased cost of key components has been noted as a driver. So for example, mirrors and receiver tubes have seen a significant cost decrease in the last 5 years, which are now beginning to be fed into some of the bigger plants, such as the Dubai plant, such as the South Africa plants. So it's really important that those types of commodities, those types of components are almost like commodity products now, especially when you are looking at information that we're receiving from developers that some of the actual plants, such as Solana in the US, were able to build a specific mirror factory and then amortize most of that in the large volume of construction. Another key part of this is commoditization, where effectively things like the steel structures and the specifics such as drives or the receiver tubes are being seen as off-the-shelf components. And so that standardization is also beginning to really help decrease some of that cost. One of the key things that especially we're looking at is understanding, for example, connecting volume of and economies of scale to cost as a driver. So for example, when you're able to build huge solar fields, for example, the 600 megawatt parabolic trough solar fields at the Dubai plant, that's a phenomenal amount of scale and purchasing power to be able to really fundamentally reduce the cost. And I'll touch upon this later on in the presentation as well. When you look at modularization, you can also then decrease the cost and also increase the cost effectiveness. And there are companies in the market today, such as 24/7 Solar and also Vast Solar, who are beginning to show that, for example, modular towers and modular fields are an effective mechanism for reduction of overall CapEx and LCOE. When we look at the operational costs, for example, reduction in water consumption, which Chris, for example, will be highlighting, is going to be another key driver, but more from the actual overall running side. That'll also include areas such as reduction in cleaning or improvements in cleaning so that either less water is needed or, for example, decreased effort is needed in the cleaning, e.g. through robotic cleaning for some types of large-scale plants. That's being seen, for example, in PV, but also in the linear Fresnel plant in France, for example, the 9 megawatt linear Fresnel plant. So these are amazingly interesting, important cost drivers, which are beginning to show each of the pieces moving towards a much decreased cost of capital and also decreased operational costs as well. And I'll highlight that my third section is really how does cost go from today into what could be a potential cost in the future. And so NREL has a product called the Annual Technology Baseline, and I'll just highlight the CSP section from that to showcase what costs could be. When we look at this, and all of this is available from the Annual Technology Baseline website, today's baseline cost is 2017, and in the US, this is important to highlight, these are potential costs for the US going forward based on both based on constant technology, mid-technology costs, and low-cost scenarios. So for example, in 2018, 2019, we're seeing a estimated cost of capital of approximately $6,500, $6,200 per kilowatt. Now, when you look at the basis of it, there's a significant amount of effort being put into gaining projections from other organizations like IRENA, like DLR, to be able to showcase that there is a cost reduction potential in the US, for example, with 10 hours of molten salt power towers technology. And so, for example, from 2021, which is when plants in the Annual Technology Baseline being built in 2018 would be realized in 2021, it is around the 6,200 odd mark, and then it could fall to $4,800 per kilowatt in 2030. And then further, based on CapEx and expansion criteria that we're adding in some of the low-cost scenarios. Again, this is just for an overall perspective, and we've shared all the information in the reporting. So, for example, that cost curve that we just showed, if you see the mid curve, the blue middle is based on the fact that there are many other projections finally being released from other organizations, which are then the basis for creating the middle assumption, but also on a cost transfer between global markets of CSP and then the US market. So again, this is really about a cost projection, which can be used in the global markets, but it should be noted that it is from a US perspective. But it is one of the additions of cost projections in the world. And this is specifically for power towers with molten salt storage. And the low originates from both IRENA, which is the Power to Change report, and also other organizations as well, and some of our own research targets. When we look at what the impact of the CapEx and operational costs have on levelized cost of electricity, the left-hand side is looking at the levelized cost of electricity in specific D&I regions, which are fair, good, and excellent. So Texas, Phoenix, and California. And this is in the R&D only scenario, which means that there is no accounting for what happens, for example, on the right, where the investment tax credit could actually reduce in the future, and therefore the levelized cost of electricity of these plants could potentially increase and then decrease. So for example, in the R&D only scenario, the LCOE could reduce in the US potentially to $55 per megawatt hour if sufficient plants can be built, and then similarly to around $47 per megawatt hour by 2050, which is pretty amazing, but is based on both today's technology and also some of the new technology advances that are happening in the markets as well. Again, all of this can be found in the annual technology baseline, and I've only highlighted the CSP section. When you look at what the expansion potential of CSP in the US could be, it's based on that type of cost projection. And I'll just give you a quick highlight of some of my other colleagues' work of what could happen if CSP could hit the Sunshot 2030 targets. And I'll explain what that is next. When we look at the overall levelized cost of electricity, and we say what is a base load and what is a peaker, I'll highlight those again, is that we, in the US, the Sunshot 2030 target from the Department of Energy is for CSP baseload electricity to hit 5 cents per kilowatt hour in the US, which is in California specifically, and then the peaker, which has shorter duration of storage than, let's say, the baseload plant at around 10 cents per kilowatt hour. This is just a scenario of what could happen if both photovoltaics and CSP hit low-cost targets, but also when they're adjoined or if different things are happening. So if PV is hitting its low-cost targets, if CSP is hitting its low-cost targets, if batteries are also involved. So it depends on the scenarios being utilized. For example, low cost of natural gas, if certain scenarios are being met or not. As you can see, there's phenomenal capacity potential up to about 150 gigawatts in the US if costs can really be reduced. So let me show you the geographical impact of that. If CSP can reduce its costs in the global markets and then in the US, there's actually a very interesting perspective that starts to happen. Markets start opening up from high D&I regions in the Southwest, in California, Nevada, Arizona, Texas, in 2030, 2040, and then going to actually places like California, Florida, North Carolina, and the southeast of the United States. Very interesting. When you look at PV, again, it actually improves from southwest to southeast, and the capacity is significant. I mean, well over 100 gigawatts could be seen in even certain areas such as Texas. It's pretty amazing stuff. What could happen, again, if these types of low-cost targets are hit. All of this can be found in another report, which is at the bottom. I just wanted to give a quick snapshot of some of my colleagues' work. When we look at how we're looking at some of the CSP benchmarking today at NREL, this is one of the reasons why we're doing this, is to be able to create understanding of both today, but also advanced technologies. So for example, right now, we are doing a detailed bottom-up perspective of large aperture troughs. And this is an update of a 2015 analysis, which looked at, again, how do you really get to that bottom-up dollar per meter squared cost? So we're using tools such as design for manufacturing and assembly to be able to break down the collector costs, but also installation, assembly, to be able to do large cost estimations of these large aperture troughs. So we're looking currently at the Atlas trough, the midterm design, and also the ultimate trough, the commercial design. The analysis is ongoing right now, and eventually the reporting will come in 2020 or 2021, more than likely. Similarly, we're also doing a bottom-up heliostat analysis to show what could the cost basis of commercially deployed technology versus the next generation, or what could be considered next generation technology, again, to provide important benchmarking of the market, but also how the market could progress in terms of technology pathways or cost reduction. So the two potential next generation heliostats are the Solar Dynamics and also the Edison heliostats seen in the picture. So again, the key metric here to be updated is the dollar per meter squared perspective in SAM, which will then be able to have the effect on the overall CapEx, overall installation of a CSP plant. As any updates are made to other components, such as the balance of plant or the receiver tubes or the site improvements, then again, they'll be reflected in SAM and also in some of the reporting that comes out from NREL. I thought I'd highlight why all of this R&D is important, because of course, from an R&D perspective, it's not only to do R&D, but it's to also reduce cost and help the technology improvements and get it to market. And I'll just highlight a quick perspective of what the Department of Energy and also what NREL are looking at for R&D pathways for significant cost reduction.
Parthiv, sorry, I hope that you know there aren't that many more slides to present, because we need to wrap up fairly soon.
Okay, so I'll talk about, perfect, thank you, Carlos. Then what I will do is, the Department of Energy is looking at high temperature pathways. Those include both low cost solar fields, but also high temperature in terms of supercritical CO2. Thank you, Carlos. And NREL, for example, are focusing on the use of high temperature molten salts. And there are three main pathways that are being considered. Again, thank you so much for the ability to give you the presentation today.
Thank you, Parthiv. Very, very interesting, your presentation. I'll switch my camera off on whilst I speak. You know, thank you for the great presentation. So I'd like to let everyone in the audience that you can ask questions. So search for the questions box. I'm sure there are, you know, a few of you online, so you must have a fair number of questions for our presenters today. And then, you know, Chris, are you ready to present?
Yes, I'll just get everything up on the screen.
So I can see your screen. If you get the presentation on full screen, then you'll be ready to go.
Okay, how does that look?
It looks good. So good to go.
Okay, so I'll just move something around on my screen. There we go. Okay, can you still see me on the webcam, by the way?
Yes.
Good, okay. Right, so, hi to everybody again. So I'm going to talk to you now about reducing water consumption in CSP plants. And this is, there are two principal ways in which we can reduce water consumption in CSP plants. One is reducing the cooling water in the power block. I'm not going to say anything about that today, important though it is. I'm going to concentrate on the water used for cleaning the mirrors in the solar field. And I'm just going to give you a couple of, I'm sorry, I'm trying to move my slide. It's not moving at the moment. I'm not sure why. Not sure why that is. Okay. So, but before I do, just a quick word about Cranfield. For those of us who don't know Cranfield University, then we're a postgraduate university in the UK, located right in the middle of the UK, near to both Oxford and Cambridge. And we're known for our research and for our postgraduate teaching. I myself work in the energy and power theme of Cranfield University. I lead the Renewable Energy Systems Centre, but my own particular research field is in CSP, and I've been doing that now for, I guess, nearly 10 years. So today, we're going to look at innovations which have come out of two EU-funded projects. These are called WASCOP and Solwat. Solwat has recently been renamed Solwaris. So before I start, I'd like to just mention my colleagues in those two EU-funded projects and my partners in those projects. And if you want to know more about anything I'm going to talk about in the next 20 minutes, then do go on to the WASCOP or Solwat websites, where you'll see much more work on reducing water in CSP plants, both in the power block and in the cleaning of mirrors. Because I'm only going to touch on that very quickly today and give you two innovations that have come out of Cranfield University. So if we think about how we can reduce the water that's used for cleaning mirrors in the solar fields, then there's two obvious ways, I guess. One is we can prevent the sand and dust from reaching the mirrors in the first place. And secondly, assuming that we are unsuccessful in that and that sand and dust does reach the mirrors, then how can we reduce the water consumption that it takes to clean those mirrors in that scenario? So I'm going to talk about dust barriers for soiling prevention, and then on a new plasma-based cleaning process, which is not something that's in the EU-funded projects, but is something that we're working on at Cranfield with a company called AdTech Europe. So you all know, I guess, quite well enough without me mentioning again, that CSP plants are in hot, dusty, arid areas where water is a precious resource. And many of the countries where CSP plants are located are highly water stressed. So anything that we can do to reduce water consumption has a benefit, a social, economic benefit to the communities, as well as a cost reduction that Parviv mentioned in his presentation. So if we look at the dust barrier first, then the dust barriers that we've been experimenting with are fence-like structures around a CSP plant. CSP plants, of course, have fences around them already. They're there for security reasons, and they're often there to reduce the wind loading on the end collectors in the solar field. We're talking about something slightly different, though, that deflects the air, reduces the velocity of the air, and in some ways carries the sand and dust either over the solar field or stops it at or near the barrier. We've been doing this so far for parabolic trough plants, but as I think you will see, you can see as we go through the slides, its applicability to heliostat fields too. We've also looked mainly at 2 meter high barriers, although full height barriers of 6 to 7 meters are also planned on the Solwatt project over the next 18 months and 2 years. The dust barriers themselves, we have these test facilities that you can see in the photograph are at the PSA in Almeria in southern Spain, one of the partners in both of these EU projects. We do a lot of experimental work outside at the PSA. Here we're actually trying to accelerate the process by using large fans to blow sand and dust at these barriers, at these, in this case, a curved barrier that you can see. And in all cases, and we have many results from these experiments taken over the last two years, we get something of the order of between 43 and 50% of the particles stopped at the barrier. These are porous barriers. The porosity is between 30 and 50%, and in this case they're made of metal, and they have advanced aerodynamic shapes depending on what we're trying to encourage the particles to do. It's probably worth me saying that a solid barrier doesn't do it. Solid barriers actually have quite a detrimental effect on airflow. They create vortices which can whip up the sand and dust from inside the plant. So the porosity is actually very, very important. The results that we got in terms of the between 43 and 50% back up work that we also done on using CFD and wind tunnels. And I'll come to that in a moment. The CFD simulations themselves, you can see, if you like, a schematic as to the concept and the extent of the analysis that we're able to carry out with CFD. So we're able to consider rows of collectors with various tilt angles. We assumed a Eurotrough in this particular case, but it doesn't have to be. And then we've carried out CFD using airflows, but now more recently using particles. So now we're using real particles in the analysis. And this particle size, by the way, is between 20 and 250 microns. So those are the particles that we've considered in size, and they are spherical too. There's the porosity. Now, if we do the analysis, then we find that the flat barriers and the curved barriers behave in slightly different ways. The flat barrier is actually more effective in the outer rows. That the curved barrier seems to work better in the rows closest to the barrier, to the edge of the solar field. Again, whether we use CFD or whether we use the experimental results, we still keep coming back to this same number, which is good to see that we're able to achieve 40 to 45% reduction in these sand and dust particles reaching the first mirror, and that the benefit of the barrier goes of the order of 30 to 35 rows into the plant. After that, then you're not really achieving any significant advantage, but that's quite a long way into the plant that we're getting a benefit from using the aerodynamically shaped dust barriers with those kinds of porosities. Tilt angle, we looked at the impact of tilt angle on those results, and there's not a huge difference. There is a difference, it is significant, but it's a small effect. By changing the tilt angle, as you can see, from 30 degrees to 150, so almost pointing upwards in that case. But you're still getting an advantage by using the barriers as you go through the day, as the tracking continues throughout the day, which again is good to see and shows that we're having a good impact with that. We also looked at, did the same analysis using wind tunnel. We built our own wind tunnel especially for this purpose, since the other wind tunnels at Cranfield are very large. So we built a slightly smaller one. And again, at all the points you can see on the right-hand side on that schematic, we were able to measure the velocities at those various points, or calculate the velocities at those various points. And again, we found that now with the wind tunnel and the CFD and the experimental results, we were able to get validation of each of those approaches with the wind speeds that we understood and particle reductions that we found right from the very start in the experimental results. And here I've just shown a picture of the wind tunnel, which we put smoke in the wind tunnel to show the various airflows, and these are very small models of troughs and barriers inside the wind tunnel that you can see on the left-hand side. And again, we were able to validate the CFD simulations with the wind tunnel results in terms of the behavior of the airflows over the barriers and over the troughs themselves. So to conclude on the dust barriers, we believe we have validated both the CFD and the wind tunnel results by experimental results outside. There is a definite advantage to using porous barriers of between 30 to 50%. They will reduce the particles downwind of the barrier by up to 45 to 50% over as many as 25 or perhaps even 30 rows into the plant. Our next work on the dust barriers is to go full size, and that will be happening on the Solwat project over the next 2 years. So they'll be 6-meter high barriers of a number of different shapes. I think there is still, the jury is still out as to the optimum shape of the barrier, as to whether it should be flat, slightly curved, or flat with lips and so on. So we have some more work to do in that respect. I just wanted to, quick change of tack, I just wanted to show 2 or 3 slides on a new concept which I thought you might appreciate. And this is work being done with the company AdTech on the plasma cleaning of glass mirrors. This might seem like an unlikely, excuse me, this might seem like an unlikely thing to do. But it's quite exciting, and I thought you might like to have a preview as to where this is going. I won't go through this slide again. This is just explaining, as we all know, the amount of water that's used to clean the mirrors in solar fields. But this particular technique is using a novel plasma cleaning process in order to become waterless in the cleaning process. And this plasma process renders the surface of glass either hydrophobic or hydrophilic, and we can almost toggle between the two by choosing the correct plasma process. This is an atmospheric plasma, by the way. I'm not going to give much detail since this is a company confidential, but the company will be at the CSP exhibition in Madrid, so you can ask them yourselves there. I will be there too. What we've done is put the plasma array, the plasma torch, on the end of a robot arm, the FANUC robot, which we have in the lab. The plasma emits a plasma jet which vaporizes the sand and dust, and we're able to impact the surface energy of the mirror in this way, and we can see that in terms of the contact angle. And very quickly, because I fear I will run out of time soon, the mirrors which had an initial reflectance of 92% were soiled in the lab, and then to a great extent, so their reflectance was very low. And then the plasma jet was passed over the sample, and you can see from the graph how the reflectance improved and was restored, in fact, depending on how many times that you that you ran the plasma torch over the surface, and also on the speed at which you ran over the surface too. The contact angle was also measured, and again you can see how the contact angle changed significantly as the number of passes increased. So in this case, we've been able to create a super hydrophilic surface, a very low contact angle with even with one plasma pass. Okay, I guess one interesting, well, there are a number of interesting questions about this technology. First of all, how scalable is it? I'm not going to say much about that today, except to say that the company is working on scaling this up. But also, how long does the effect last for, I suppose, when you've created this super hydrophilic surface? And initial results show that the effect lasts for about 1 week. But then the plasma conditions have not been optimized, so I would expect that to improve in the future. And remembering that most solar mirrors are cleaned on average between maybe once every week or 2 weeks, depending on the degree of soiling in those real plants. So just to summarize the plasma cleaning concept, then we have a method, it appears, that we can render a surface, a toggle between hydrophobic and hydrophilic, which could then have impact in terms of anti-soiling or self-cleaning, depending on the degree of moisture on the surface, depending on when it rains and so on. But the plasma process not just only toggles between those, it actually will remove the soiling too, which is extremely exciting. This is obviously at the early stage of development. It's not optimized. The company and indeed Cranfield and its partners are working hard to improve this technology. And our next stage will be to build and test a prototype and then try it out for real on real solar fields in real power plants where there is a very arid and dusty condition. And I'm looking forward to seeing how that progresses. And yes, if anybody is interested in collaborating on this, then they're very welcome. I'd just like to say thank you to not only to my EU projects and partners, but also to my colleagues, especially to Peter King and Adam Bennett, who did most of the work on with Heather Almond, Munia Karim on these slides, and on the work, particularly the work at the PSA. So thanks very much to them. I'm presenting their work here today. Thank you.
Thank you very much, Chris, for your presentation. So I think the three of us could come up now on our webcams, so the audience can see us as we speak. And we have quite a lot of questions, actually, which up front I have to say that we won't be able to answer all of them. But you know, if you are around in Madrid in November, on the 19th and 20th of November, there will be the CSP Madrid 2019 conference, and there you'll be able to meet not only you know, the three of us, but many others who work in CSP and who would definitely be able to answer your questions as well. Otherwise, we'll do our best to answer some of them now. So before we get to you know, I'd like to thank both of you for your presentations on, you know, two very different aspects of CSP, but very interesting, both of them. I want to get the sort of like the big elephant in the room. I want to like point out at it and just get it out of the way. So you know, CSP costs, we saw that they have decreased, yet they remain relatively expensive compared to PV. So CSP must have something that going for it, otherwise, you know, no one would be considering it. So why are countries like, you know, Dubai and Morocco and many others still building CSP plants, given that, you know, PV now, last week they had a sub 2 cents bit, and that's crazy low. So why is it that these countries are still considering CSP and not just PV, and that's it? I can't hear you, Parthiv. Yeah, now I can hear you.
I was going to say, Chris, do you want to take a crack first, and then I'll jump in after?
Probably more in your area than mine, so I'll let you start.
I was going to say there are different, there's sort of water consideration reasons, but there are many countries like Morocco and Chile and South Africa which are looking at CSP still, because whilst low-cost PV is fantastic, PV with battery right now is still seen as the very relatively new but also expensive technology, and also it's unclear how the lifetime of these batteries are going to be and the replacement rates of large-scale battery storage. And so CSP is really offering a phenomenal balancing of the electricity from PV as well as wind to be able to give grid stability, grid flexibility, and also making sure that the average cost of electricity is our PPAs are really low. And so that's one of the reasons that CSP is highly valuable, is to be able to balance that low cost, let's say, low cost PV, which is also time limited as well, or day limited, right?
And,
yes.
and variable, right? So sorry, Chris.
Yeah, it's all about dispatchability for me. So yes, you're right. It's about the fact that you want to be able to dispatch the energy when the consumer wants it to meet the demand, not when you produce it. And the thermal storage option of the CSP is something that at the moment PV cannot match. It can produce electricity cheaper than CSP, but not necessarily when you want it. So it's the thermal storage option that's the big advantage, the dispatchability of CSP electricity, which makes it so valuable. I think that's the main advantage.
So right, thank you very much for your answer. So yeah, it seems that you have a situation where you could PV and CSP with thermal energy storage could complement each other. So you could have PV producing power for for the day peaks, as it were, like around midday, and then in many places you have, and Spain, for example, is one of them. You have a very steep peak at night time, and you can't really service that with PV. So that's where CSP with thermal energy storage comes in. We obviously batteries come into the question because they provide a similar service to thermal energy storage. So for people who are in the audience, so what are the how are they different? And Parthiv, do you have an idea of how much would it cost to have an equivalent sort of like bulk power storage, storing bulk power produced from renewables in batteries compared to CSP with thermal energy storage?
Sure. So it's worth highlighting that, for example, with batteries right now, even though they're reducing in cost, the ability to provide 100 megawatt hours, let's say, which is 10 hours of storage, or large scale utility scale storage, is still 3 to 4 times more expensive than current molten salt storage, for example. So there is a huge amount of cost associated with projects. I should say that each is project specific as well on how much storage you want. But the thing is that low cost thermal energy storage for the next decade is expected to be cheaper than batteries and the replacement. So NREL plus other organizations are doing a lot of work on battery technology, but also costing and replacement and How long will these systems last? It's also important to highlight that batteries are great for very short duration demand service meeting those demand services. So for example, within the minute to hour time scale rather than the hours to day time scale that typically CSP can do. So there are differences, and that's something that the markets are beginning to understand, is that each energy storage has a different time span in which it should be or could be best utilized. So just knowing that a battery can do 2 hours or 3 hours or 4 hours doesn't necessarily mean that it's best suited for that repeatedly for 25, 30 years, for example.
Yeah, I agree. It's about 5 times, the numbers I've seen, it's about 5 times more expensive to store electricity than to store the equivalent kilowatt hours in heat. And both are improving, but we're getting better at improving heat storage too. So that multiplier is not likely to be significantly different in the next 10 years. So there is still the advantage in storing heat over storing electricity from a cost point of view.
Right, it's a very, very good point. And just the last, just to answer a couple of the questions that have come on the questions panel. So they ask whether the cost estimates are given for high capacity plants and whether they include energy storage.
Is that on the battery side, I suppose?
No, that's on the CSP side that you mentioned. So are they for like large utility scale power plants, and do they account for the thermal energy storage component?
Yes, the CapEx figures I was showing earlier are based on the large plants, 50 megawatts and above, 50 to 100 megawatts. And a lot of the data has been compiled by New Energy Update, which is a great resource, other resources as well. And yes, we're looking on average 8 to 10 hours, or even in some cases 15 hours of storage, so huge amounts of storage, as well as the solar field needed. So yes, it's an overall CapEx for large capacity factor plants.
Okay, thanks. And Chris, there is a question for you here that reads, what is the overall impact of cleaning on costs?
Well, that's a good question. That depends on your attitude to cleaning the mirrors. In many cases, the mirrors are cleaned on a routine basis on a rotor system, regardless of their soiling. So there is an assumption being made here that that is not always the case. That you may only clean your mirrors when they need to be cleaned. If that's the case, then you can look at reducing your water consumption by up to 50% for cleaning the mirrors, the water spent cleaning the mirrors anyway. And that depends, of course, on how much you pay for your demi water, which varies hugely across the world as well. So hard to put numbers on that, but I would just say that you could save up to 50% of the water that you use to clean the mirrors could be saved by using, for example, the dust barrier as a simple example. But putting a cost on it would depend on your local conditions and your local labor costs and your attitude as to how often you clean the mirrors.
So, I mean, a lot of the CSP plants that are being built now are being built in the Atacama Desert, which is the driest place in the world. Then you have a huge project in Dubai. So what I'm trying to say is there are very places where water is scarce. So, how could you, are there waterless cleaning solutions that you can use? Because these places are very dusty, and they're also, you can't really afford to use water there.
That's right. That was the reason why we've been looking at the plasma cleaning technique, which uses no water at all. So approaches like that are quite exciting, and yes, at the moment, if you're using brushes and water, which generally are used, then the brushes alone simply are not effective. So you have to use water. So yes, that's what drove us to looking at alternative, somewhat radically new and innovative technologies, and I'm sure there will be others too.
If you think in those, I don't know about Chile, but definitely in Dubai, you'd be looking at cleaning your plant with desalinated water, how expensive that would be. So have you tried your plasma technology on site now? Do you have a test now, an ongoing test?
We're about to do that. We're just coming out of the lab, so we hope to be doing outdoor tests. It will be next calendar year now.
Okay, right, good. So, well, I'm not really sure. We're already over the allotted time, you know, and it's already a couple of minutes past. I don't know if you'd like to share any last words about, you know, what it would take really for CSP to at least really, well, to reduce the levelized cost of energy and become more competitive, and you know, what are the key aspects driving the attractiveness of CSP, just before we close the session?
Well, I'd just like to say a few words about, because I'm mainly concerned in this discussion about water consumption, so I will just conclude, I think, in saying that I've only spoken about water consumption on the cleaning processes, but on the cooling side and the power block, in order to cool the turbine and so on, there is much work going on dry cooling. Normally you would pay a penalty with the efficiency loss by dry cooling, but there are ways in which you can get around that too. So from the water consumption point of view, I think both in cooling the power block and in cleaning the mirrors, we are making significant contributions as part of these EU-funded projects, WasCOT and Solwat, and I do yet again say to people, go and have a look at those if you want to see all the things that are happening on water consumption reduction for CSP plants. There is a cost implication of that, but as you quite rightly point out, Carlos, there is a socio-economic element to this as well, in that these countries are highly water stressed, and any water that you use is depriving that water from people for drinking or for agriculture. So it's an important element to consider, I think, as well as just cost.
Right.
Thanks, Chris. In terms of how, let's say, to make it more attractive as a technology, the question of whether it's on its own is probably not the right question anymore, where you can use the benefit of the fact that PV is very cheap, excellent, and then you can use the dispatchability aspect. So markets which need dispatchability will certainly gravitate and utilize the technology. And so therefore, to increase that attractiveness, I would say there are certain things such as increased scale, increased supply chains, especially in the local markets, improvements in some of the component costs, but also, like in PV, increasing the standardization, increasing the modularization to be able to make it very cost effectively. And that's actually coming. Because the risk is being decreased in the technology, and now PV with CSP is being utilized at scale, that to me is going to be a phenomenal improvement in the attractiveness of CSP as well. So I don't think we should look at it only as a CSP only technology anymore. It's that time may have changed, but I believe that the perspective of CSP plus PV or CSP plus other hybridization options, geothermal and so on, would really help in that manner where dispatchability is needed.
Right, it's more of the system level consideration, right? It's no longer just well, I don't think, you know, a power system should rely on one technology. That'd be putting all your eggs in one basket, which is not what power planners should do. Right, well, I think we're going to close the session today. I'd just like to remind you that coming up in November 19th and 20th, there will be an event on concentrated solar power in Madrid, which is CSP Madrid 2019, and there you'll be able to see NREL, Cranfield University, and many other experts as well. We'll be talking about CSP, but also we'll be talking about concentrated solar heat for industry and other aspects of CSP. Storage, I think, will feature prominently. So, well, I hope you can make it to Madrid and see us there. Right. So, thank you very much. Have a good day.
Thanks so much.
Bye.
Bye.
Thank you. Bye.